Molecular clouds represent the densest parts of the interstellar medium in galaxies, playing a crucial role as the birthplaces of stars and serving as key components in galactic evolution. These massive collections of gas and dust undergo a complex life cycle from formation to destruction, influencing the structure and energetics of their host galaxies. Molecular clouds are not static entities but rather dynamic structures that form, evolve, and eventually disperse, completing a cycle that typically spans tens of millions of years. Molecular clouds begin their lives within the diffuse interstellar medium, primarily in regions dominated by atomic hydrogen known as the warm neutral medium. The transformation from this diffuse state to dense molecular clouds involves several physical processes working in concert. Two primary mechanisms have been identified for molecular cloud formation: the collision and coalescence of smaller gas clouds, and gravitational instability or swing amplification effects in the galactic gas layer. These processes don't operate in isolation, but often work together to concentrate interstellar gas into regions dense enough for molecular hydrogen to form and survive. The formation of molecular clouds is not a slow, gradual process, but rather occurs relatively rapidly on galactic timescales. Estimates suggest that the formation time for giant molecular clouds is approximately 50 million years, which is not substantially longer than their overall lifetime of around 20 million years. This relatively short formation timescale indicates that cloud formation must be an efficient process, likely driven by galactic-scale dynamics, rather than slow accretion of material. Observational and theoretical evidence points to colliding flows as a significant mechanism for molecular cloud formation. When streams of interstellar gas collide, they create compressed regions where thermal instabilities can be triggered. These instabilities cause the gas to cool rapidly and increase in density, creating the conditions necessary for molecular cloud formation. The efficiency and timescale of this process depends significantly on the velocity of the colliding flows. Simulations show that faster flows with velocities around 13.6 kilometers per second can form star-producing molecular clouds in just 4.4 million years, while slower flows of 6.8 kilometers per second require approximately 16 million years to produce the same outcome. The chemical evolution of forming molecular clouds follows a distinct pattern, with molecular hydrogen, H2, forming well before carbon monoxide, CO, the second most abundant molecule and primary observational tracer of molecular gas. This creates an interesting observational challenge, as substantial amounts of molecular gas may exist in a dark phase before becoming detectable through traditional CO surveys. In simulations of cloud formation through colliding flows, H2-dominated regions form anywhere from 3 to 10 million years before star formation begins, depending on flow velocity. In contrast, CO-dominated regions appear much later, typically only about 2 million years before the onset of star formation. The initial phase of molecular cloud formation involves rapid cooling of the compressed interstellar gas. For slow-velocity flows, this cooling phase completes in approximately 4 million years, while faster flows complete cooling in just 1.5 million years. During this period, the temperature drops dramatically while density increases, setting the stage for the formation of molecular species. Following this initial cooling, the cloud enters a phase where turbulence dominates over self-gravity. This turbulent phase lasts around 10 million years in slow flows and 2.5 million years in fast flows, during which the cloud develops significant internal structure, but most of this structure is not yet gravitationally bound. Once formed, molecular clouds exhibit a wide range of sizes and masses. Giant molecular clouds, GMCs, can span approximately 100 light-years and contain up to 6 million solar masses of material. The gas within these clouds is significantly colder and denser than the surrounding interstellar medium, with typical temperatures ranging from 10 to 20 Kelvin in the dense regions. This dramatic cooling is essential for enabling the gravitational collapse that eventually leads to star formation. The internal structure of molecular clouds is complex and hierarchical, characterized by significant density contrasts. Rather than being uniform spheres of gas, molecular clouds contain intricate networks of filaments, sheets, and clumps. The densest portions can reach number densities of thousands to millions of molecules per cubic centimeter, while the more diffuse regions may have densities only 10 to 100 times greater than the ambient interstellar medium. This structured nature results from the interplay of turbulence, gravity, magnetic fields, and thermal processes operating within the cloud. One of the most striking features of molecular clouds is their ubiquitous filamentary structure. These filaments play a crucial role in the star formation process. Dense molecular filaments fragment into gravitationally bound cores, which serve as the immediate precursors to stars. The fragmentation process is influenced by multiple factors, including continuous accretion of gas, geometrical bending, and magnetic fields, all of which control the detailed manner in which filaments break into smaller units. Observations of supercritical filaments have revealed quasi-periodic chains of dense cores with spacing comparable to the filament width, often containing embedded protostars with associated gas outflows. The turbulent nature of molecular clouds creates supersonic motions within the gas, resulting in shock waves that compress material into dense structures. These turbulent compressions, combined with thermal instabilities, generate the complex substructure observed within molecular clouds. Initially, much of this substructure is not gravitationally bound, but is instead maintained by a balance between turbulent pressure and self-gravity. Over time, some regions become dense enough for gravitational forces to overcome turbulent support, leading to further collapse and eventually star formation. After a molecular cloud forms, it typically undergoes a phase where turbulence is more important than self-gravity in determining its internal structure. During this period, which lasts about 10 million years in slow-forming clouds and 2.5 million years in fast-forming ones, the cloud develops significant internal substructure through thermal instabilities and turbulent compressions. Although dense regions exist within the cloud during this phase, the majority are not gravitationally bound and will not collapse to form stars. The transition from a turbulence-dominated to a gravity-dominated cloud marks a critical point in molecular cloud evolution. This transition occurs when some regions within the cloud become dense enough for self-gravity to overcome turbulent support, thermal pressure, and magnetic forces. These gravitationally bound cores begin to undergo runaway collapse, dramatically increasing in density while continuing to cool. This transition happens relatively quickly on astronomical timescales, with gravitational collapse proceeding on free-fall timescales of roughly 1 million years for typical core densities. As certain regions within the molecular cloud become gravitationally unstable, they begin to collapse more rapidly than their surroundings. This collapse isn't uniform throughout the cloud, but instead occurs in localized dense cores. The collapse accelerates as gravity becomes increasingly dominant, following a roughly free-fall timescale that depends on the initial density of the collapsing region. During this collapse, the gas continues to cool until it reaches temperatures around 10 Kelvin, which is typical of observed star-forming cores. The formation of gravitationally bound cores represents the beginning of the star formation process within molecular clouds. These cores are the immediate precursors to protostars and typically have masses ranging from a fraction of a solar mass to several solar masses. The distribution of core masses within a cloud is thought to be related to the initial mass function of stars, suggesting that the properties of the molecular cloud directly influence the characteristics of the stellar population that will form from it. Star formation begins in earnest when gravitationally bound cores within the molecular cloud undergo runaway collapse. As a core collapses, its central density increases dramatically, while the temperature initially remains low due to efficient cooling. Eventually, the innermost region becomes opaque to its own radiation, causing the temperature to rise and forming a protostar at the center of the collapsing core. A protostar is essentially a hot, rotating ball of gas that will continue to grow by accreting material from its surrounding envelope. The collapse of a molecular cloud fragment into a protostar follows a predictable sequence. As gravitational potential energy is released during collapse, it is converted to heat, increasing the temperature and pressure of the fragment. This process continues until the fragment condenses into a protostar, which continues to grow through accretion of surrounding gas and dust from the molecular cloud. These protostars are heavily obscured by surrounding dust and are therefore most readily observed at infrared wavelengths. Space-based infrared observatories particularly the Wide Field Infrared Survey Explorer, WISE, have been instrumental in identifying numerous galactic protostars and their parent star clusters. After a protostar forms, it continues to evolve by accreting material from its surroundings, gradually reaching its final mass and becoming what astronomers call a pre-main sequence star. The subsequent development of this young star is primarily determined by its mass. Stars are typically compared in terms of solar masses, with 1.0 m representing the mass of our Sun. As accretion slows and eventually ceases, the young star contracts under its own gravity, causing its core temperature and pressure to increase. When the core becomes hot and dense enough to ignite nuclear fusion of hydrogen into helium, the star reaches the main sequence phase, which represents the longest period in a star's life. The time required for a protostar to evolve into a main sequence star depends strongly on its mass, with more massive stars evolving more quickly. Low-mass stars may take tens of millions of years to reach the main sequence, while high-mass stars can do so in less than 1 million years. An important aspect of star formation within molecular clouds is that only a small fraction of the cloud's mass is converted into stars before the cloud is dispersed. This fraction, known as the star formation efficiency, typically ranges from a few percent to about 10% in most molecular clouds. The relatively low efficiency suggests that various processes, particularly feedback from young stars, prevent most of the cloud material from forming stars before the cloud is dispersed. Star formation in molecular clouds often produces clusters or associations rather than isolated stars. The densest regions of molecular clouds can give rise to bound star clusters, where hundreds to thousands of stars form in close proximity. Less dense regions tend to produce more loosely bound stellar associations or dispersed populations of stars. The clustering properties of newly formed stars reflect the hierarchical structure of their parent molecular cloud and provide important clues about the cloud's physical properties and dynamics during the star formation process. Once stars form within a molecular cloud, they begin to influence their surroundings through various feedback mechanisms. Young stars, particularly massive ones, produce intense radiation, powerful stellar winds, and eventually supernova explosions that inject energy and momentum into the surrounding molecular gas. This feedback dramatically affects the evolution of the parent molecular cloud and can ultimately lead to its destruction. The feedback from newly formed stars is a crucial factor in determining the lifetime of a molecular cloud. Observational evidence indicates that molecular clouds do not survive without major changes for more than about 20 to 40 million years. This relatively short lifetime is directly supported by the age range of young stars associated with molecular clouds, which is typically only about 10 to 20 million years. This time span is comparable to the internal dynamical timescales of large molecular clouds, suggesting that these structures evolve on timescales set by their own internal dynamics. The dispersal of molecular clouds is closely linked to the star formation process. Subgroups of massive OB stars older than 10 million years no longer contain significant amounts of gas or dust, indicating that the gas from which such groups formed is cleared away within this time frame. Similarly, clouds or portions of clouds that form star clusters are dispersed in a comparable period, as evidenced by the absence of molecular gas within 25 parsecs of clusters older than 10 million years. The mechanisms responsible for cloud dispersal include photoionization from massive stars, which heats the gas and creates expanding high regions, radiation pressure that directly pushes on the gas and dust, stellar winds that sweep up molecular material, and supernova explosions that can disrupt entire cloud complexes. These processes work together to gradually erode the molecular cloud from the inside out, beginning in the vicinity of the most massive stars and eventually affecting the entire cloud. The energy input from these feedback processes can be sufficient to unbind the cloud gravitationally, causing it to expand and eventually disperse back into the more diffuse interstellar medium. Several lines of evidence support the conclusion that molecular clouds have relatively short lifetimes. One key observation is the scarcity of non-star-forming molecular clouds. Very few of the largest molecular clouds show no signs of star formation, and the total number of non-star-forming clouds of all masses is roughly comparable to the number of star-forming clouds. This suggests that there is no extended period between cloud formation and the onset of star formation. The time between cloud formation and star formation is brief enough that we rarely catch clouds in a pre-star forming phase. Given these observations, researchers estimate that the total lifetimes of molecular clouds cannot exceed twice the period of active star formation within them, leading to lifetime estimates of approximately 20 to 40 million years. This relatively short lifetime contradicts earlier ideas that molecular clouds might be supported against gravity in quasi-equilibrium configurations for many dynamical times. While virial balance is often roughly satisfied in larger clouds, this does not preclude rapid dynamical evolution of these clouds or the parts of them that form stars. Molecular clouds do not exist in isolation, but are integral components of the larger galactic ecosystem. Their formation, evolution, and destruction are influenced by galactic scale processes, such as spiral arm passages, galactic shear, and interactions with other clouds. A comprehensive theory for molecular cloud lifetimes must consider these environmental factors, which can either extend or shorten a cloud's existence depending on local conditions. The lifetimes of giant molecular clouds are affected by several dynamical processes. Gravitational collapse, which leads to star formation and eventual cloud destruction through stellar feedback. Galactic shear, which can tear clouds apart. Spiral arm interactions, which can compress or disrupt clouds. Epicyclic perturbations from orbital motion in the galaxy. And cloud-cloud collisions, which can trigger star formation or lead to cloud mergers. The relative importance of these processes varies with location in the galaxy, leading to environmental dependence of cloud lifetimes. Interactions between molecular clouds represent another important aspect of their life cycle. Cloud-cloud collisions can trigger compression and shock waves that enhance star formation within the colliding clouds. These collisions can also lead to cloud mergers, creating larger complexes, or to partial disruption, generating smaller cloud fragments. The frequency of such collisions depends on the local density of clouds within the galaxy and their relative velocities. The building of large clouds from smaller ones through random collisions and coalescence has been suggested as one mechanism for forming giant molecular clouds. However, this process alone would predict formation times of at least 100 million years for giant molecular clouds, which is longer than observational constraints suggest. This indicates that other processes, such as large-scale galactic dynamics, must play a significant role in accelerating cloud formation. The chemical evolution of gas throughout the molecular cloud life cycle offers important insights into cloud formation and destruction processes. The transition from predominantly atomic gas to molecular gas requires sufficient density and dust shielding to protect molecules from dissociating radiation. Molecular hydrogen, H2, forms first on the surfaces of dust grains, but it is difficult to observe directly in cold gas. Carbon monoxide, CO, which forms later, serves as the primary observational tracer of molecular gas. As a molecular cloud forms, it passes through a phase where it contains significant amounts of H2 but little CO, making it difficult to detect using traditional observational techniques. This dark gas phase can last for several million years. In simulations of cloud formation through colliding flows, H2-dominated regions form 3 to 10 million years before star formation begins, depending on the velocity of the flows. CO-dominated regions, which are more easily detectable, appear much later, typically only about 2 million years before the onset of star formation. The chemical composition of molecular clouds evolves over time, with various molecular species forming at different rates depending on local conditions. Some molecular abundance ratios can serve as chemical clocks that provide information about the age of different regions within a cloud. As clouds disperse, the molecules are either returned to the interstellar medium or destroyed by radiation, completing the chemical life cycle of the cloud material. The chemical complexity that develops within molecular clouds is important not only for understanding cloud evolution, but also because it sets the initial chemical conditions for protoplanetary disks that form around young stars. The molecular inventory of a cloud can influence the composition of the planets that eventually form from these disks, establishing a direct connection between molecular cloud chemistry and planetary system formation. Studying the complete life cycle of molecular clouds presents significant observational challenges. The evolution of an individual cloud occurs over millions of years, far too long to observe directly. Instead, astronomers must piece together the evolutionary sequence by observing many different clouds at various stages of their development. This approach is similar to understanding human development by studying many individuals of different ages, rather than watching a single person grow from infancy to old age. Different observational tracers are sensitive to different phases of the molecular cloud life cycle. Atomic hydrogen observations trace the diffuse precursors to molecular clouds, while observations of CO and other molecules reveal the dense molecular phase. Young stellar objects and their distribution provide information about the star formation history within the cloud, while expanded HII regions and dispersed clusters indicate the final stages of cloud destruction. Computational simulations have become essential tools for understanding molecular cloud evolution. These simulations allow researchers to follow the time evolution of clouds from formation to destruction, including complex processes such as turbulence, magnetic fields, chemistry, and stellar feedback. Recent simulations have self-consistently modeled the formation of molecular clouds in colliding flows, including time-dependent chemical networks that track the formation of key molecular species like H2 and CO. These numerical models confirm the relatively short lifetimes of molecular clouds and provide detailed information about the sequence and timing of events during cloud evolution. They show that in cloud formation through colliding flows, star formation begins after about 16 million years for slow flows, and after only 4.4 million years for fast flows. The simulations also reveal that CO-dominated regions, which would be identified as molecular clouds in observational surveys, form only about 2 million years before star formation begins. The life cycle of molecular clouds encompasses a complex sequence of processes operating on timescales of millions to tens of millions of years. From their formation in the interstellar medium through colliding flows or gravitational instabilities, through their evolution as turbulent, hierarchically structured entities, to their eventual destruction by stellar feedback. Molecular clouds play a central role in the star formation process and the broader galactic ecosystem. Current evidence suggests that molecular clouds have relatively short lifetimes, typically not surviving without major changes for more than about 20 to 40 million years. Their formation appears to be a rapid process on galactic timescales, with formation times comparable to their overall lifetimes. Star formation begins relatively quickly after cloud formation, with little or no dead time between these phases. The chemical evolution of clouds includes an early phase dominated by dark molecular gas that may be difficult to observe using traditional techniques. As our observational capabilities and computational models continue to improve, our understanding of molecular cloud evolution will undoubtedly be refined. However, the general picture of molecular clouds as transient, dynamically evolving structures that form, create stars, and disperse on relatively short timescales appears robust based on current evidence. This dynamic view of molecular clouds has important implications for our understanding of star formation and galaxy evolution as a whole, highlighting the interconnected nature of processes operating across a wide range of spatial and temporal scales in the cosmos.